And hello, everyone. I'm glad to be here, and I'm from Ethiopia. I'm going to present the thesis I did for the AMI Master's Program, African Masters in Machine Intelligence Program at the African Institute for Mathematical Science, based in Rwanda, under the supervision of Professor Costas. And the title is Guiding StyleGAN to Generate Labeled Synthetic Face Image Dataset for Underrepresented Group. In recent years, deep learning has been successful in many machine learning areas, including computer vision, natural language processing, and speech recognition. And training of large deep learning model is also possible due to the recent development of high-performance hardware. However, deep learning model often have large set of trainable parameters, and it requires a large data set for training. So one of the limitations of deep learning is that it requires a lot of data sets, and in most cases, labeled data sets. Beside that, for a machine learning model to generalize well from the data using the training set to any unseen data from the problem domain, it's well understood that the data needs to be sufficient size and representative of the real-world use. But unfortunately, large-scale data sets, which are currently used in the face image domain, are often collected without consideration of demographic distribution, and they are biased towards certain demographic distribution. Due to this, in many real-world data sets, some groups are overrepresented and others are underrepresented. Of course, bias can creep into AI system in several ways. And training data is one of the main cause for introducing bias in artificial intelligence system. As artificial intelligence system learn to make decisions based on the training data we use to train our model. So when we pay a little attention to how the data is collected, processed, and organized, there will be a lack of geodiversity, which incidentally produce data that leads to gender, ethnic, and cultural bias. So this uneven distribution and bias in the dataset lead to a biased model. A suitable technique to reduce the bias in machine learning and artificial intelligence system is clearly using diverse dataset, which is well distributed across all demographic groups. Again, collecting and labeling large-scale datasets, it poses another challenge. But to deal with this challenge, synthetic data generation and active labeling has been used. And this method actually reduces the cost of manual data collection and labeling. So we can use synthetic data that computer simulations or algorithms generate as an alternative to the real-world data, which is inexpensive. Speaking of synthetic data generation, a lot of survey shows that generative adversarial networks, or GANs, are getting traction in many sectors to create synthetic data. For example, GAN-based architecture for medical images, one of the example, and also American Express studied ways to use GANs to create synthetic data. Refining its AI model that detect fraud is another example. What are GANs? GANs are a class of machine learning frameworks designed by Ian Goodfellow and his colleague in 2014. They are deep generative models, and as you can see from the image, we have two networks in this architecture. We have two networks, namely generator and discriminator, which compete one against the other. The task of the generator network is to generate synthetic data that imitates the real data to trick the discriminator network. And the role of the discriminator network is distinguishing the fake image from the real one. However, GANs has its limitation. First, they are limited to small data set size, and they also have low resolution image generation. Due to this, generating high resolution image and controlling the attribute of the generated image has been challenging task. In the year 2018, NVIDIA has built a style-based generator architecture for generative adversarial network, which is called StyleGAN. StyleGAN is an extension to the GAN architecture that advanced the generator model, which generates synthetic data. And it has proved to tackle the two challenges of GAN by building style-based GAN architecture to generate high-quality image and by disentangling the latent factor of variation. It has also been trained on the Flickr Face HQ dataset, and it has shown that it can generate high-quality photorealistic synthetic human image, face images. Also, disentangling the latent factor of variation in StyleGAN has enabled the guiding generation of images possible, which is the main reason we have chosen this architecture to build our idea on top of it. Here on the figure, you can see the amazing progress of GAN on human face image generation. So for around 5 years, you can see really amazing progress on how of GAN on the face image generation. And here are the sample image generated by the StyleGAN model. And also the table shows the generated image distribution across different race groups. To make a concrete justification, we have randomly generated 10,000 face images, and the following statistics show the number of face images for each race. As you can clearly observe from the statistics, one problem with StyleGAN architecture is unbalanced face image generation among different races. The distribution of image being generated are often biased towards some group. So the main as you can see, we have only 400, we have only 882 Asian face and 449 black face and 6,837 white face. So this clearly shows the distribution of the image being generated are often biased towards some group. So the main aim of this research is to generate images that are uniformly distributed across different demographic groups by guiding the generation of image from StyleGAN model. And the contribution of the research is twofold. First, using StyleGAN, we generated a high-quality large-scale face image dataset that is distributed uniformly across different demographic groups. And the second contribution is we annotated the datasets for different downstream tasks like emotion, eye state, smile, gender, and race labels. We divide the task of synthetic face image generation and labeling into different pipelines. And the first step was to train race classifier model that classify an image into one of different race groups. We trained our model for the following race group: Black, Asian, White, Indian, and other. But the setup is robust and can be extended to any number of groups we want. And the second step was generating and labeling high-resolution face image. As it is shown in the figure, first random vector from 512 dimensional normal distribution are generated and fed to StyleGAN model to generate the face image. And the generated image then are passed through the race classifier model to get the race label of the generated image. And the third step was training the logistic regression that classifies the StyleGAN input space. As I have mentioned earlier, the StyleGAN model enables manipulation of the image generation. The factor of variation are disentangled, which means moving a small distance in a certain direction changes only a specific or a small set of features. We have actually proved this in our work while generating image for some race. So using the data set generated, here we have three information about the data, the input vector, image, and the race label of the image. For each race, one versus the rest, logistic regression model was trained to classify the input space of the StyleGAN model into positive and negative region. And in this work, we call this model logistic classifier. In this figure, I have tried to demonstrate the parameter vector in the hyperplane. For each race, logistic classifier parameter vector is used to compute a vector perpendicular to the hyperplane of the classification. This vector is used to guide the generation of the image from StyleGAN by maximizing the probability of generating face image with a given race. And the race classifier that I have mentioned earlier, the race classifier model is used to verify if the generated image are from the group of interest or not. If the image is from the group of interest, it will be saved. Otherwise, it will be discarded. For example, if we want to generate blackface, the direction pointed by the parameter vector is perpendicular to the hyperplane, and it's also the direction that maximizing finding the latent feature vector that will generate blackface image. So using this fact, we can randomly choose a random vector from the latent input space, and we added the parameter vector of the logistic classifier to the random vector before feeding it to the StyleGAN model. So this way one can generate as much as data they need with a specific feature for a specific demographic group. The table shows the number of images for each race when guiding is used. Here, 1,000 images per each race have been generated. And as you can see in the table, the number of the image for each underrepresented group have been increased, and the bias is highly reduced. Here are sample images, sample face images of specific race that are generated by guiding StyleGAN model. I tried to show a sample image. For example, for black face, 633 image has been generated from 1,000 image, and 423 Asian face has been generated. And this shows the bias is highly reduced. As I mentioned before, the second contribution of the research was that we have annotated the datasets for different downstream tasks. We have trained a deep neural network for downstream tasks. We have built CNN model for emotion classification, eye state detection, smile detection, mask detection, and gender recognition. In this research, we built a robust face image dataset that is well distributed across different racial groups by generating and labeling a synthetic dataset. Of course, there are some improvements which can be made in the future. We have demonstrated how to guide StyleGAN to generate face image with specific skin color. And this can be extended to face image with specific feature, such as happy face, closed eye face, engaged face, and so on. And generating face with a specific feature can be also speed up by fixing the latent feature vector around a region with a small radius. This can be done by randomly sampling a latent vector, then adding a directional parameter and fixing the vector around this new point. Then by moving a small distance from this new point, one can generate many faces with similar feature. So the baseline model can be generated on the dataset we generated. Baseline model can be trained on the dataset we generated. And also our dataset can be used to measure how much a model trained on a face-related task can perform on a uniformly or well-distributed dataset. Thank you so much for your attention, and let me know if you have any kind of question.
Thank you so much, Kidist, for this very interesting talk. This is indeed a problem that made the headlines of a lot of newspapers, and that's great that you're trying to find a solution to it. We do not have a question in the chat, so I have one. You showed in your slide that you're building a DNN on top of the GAN that you're with what you're generating your images in order to classify them. And one of the classes is others. So don't you think that this class could already create a bias without even training the model for the extreme underrepresented classes?
To train our race classifier model, we use first we train this model with UTK face data image dataset, which contain race level, and we fine-tuned a pre-trained VGG face model to train the race classifier, and it works very well, and we have got a good accuracy to do this classification. And finally, we use our own model that has generated from the StyleGAN architecture, so that won't be a problem.
Great, thank you for your answer. We have another question in the chat from Wissam, who says that it's very interesting. And the question is the code available somewhere?
Yes, it's on my Git repo, and I will put for public for both the dataset and the code very soon.